So as mentioned before, we are going to use this chart to do this calculation over here. Okay, so we are going to determine the factor of safety with respect to yield. Okay, so this question give a hint. Since the factor of safety must be applied to the load P, not to the stress, use figure 10.23 to determine Py. So this is figure 10.23, okay, which is the graph on the right hand side. Right, so the first thing we know is that the load, okay, so if we look at this over here, the load P along the y-axis, so I'm going to call it Py. So I'm going to change this to Py because it's about the y-axis. So Py, small y, okay, not big y. Py, which is the applied load, is equal to 175 times 10 to the power 3. Okay, and the next thing we're going to find out now. We have to observe our axis. Okay, so this is our. So you look at here. This is x, this is z, and this is y. Okay, so if we look at this table over here, okay, I'm going to make this table bigger so we can see better, because term test I'll provide you a table like this. Right. So from this table, we know that this axis is different. Okay. So this is x, correct? But relative to our transformation to the figure with the load, over here is not our yy, but rather our what? Our zz. Okay. So you change this to zz. Okay. Just change this about x is zz. Okay. That's it. Okay. So now, this question is very different from the one before, okay, in the sense that they don't tell us which axis buckling will occur. Do they? They don't tell us, right? So when or which is the axis buckling will occur? So we look at the II value. Okay, we look at the second moment area. So the second moment of area about ZZ, sorry, about XX is 70.8. Okay. The axis in the ZZ, the second moment of area is 6.95. Okay. So you write down here, buckling, okay, or you write down here, IZZ or IXX is equal to what? You go over there, IXX is equal to 70.8 times 10 to the power minus 6 meter 4. IZZ will be equal to 6.95. Yep, 6.95. So therefore, select the lower I value. Okay. So what does it mean? So use IZZ is equal to 6.95 times 10 to the power minus 6 meter 4. Why we use this IZZ is because the buckling will occur about the Z axis. So what do I mean by that? Okay, so I'm going to sketch for you the deformation pattern. So the deformation pattern I'm going to sketch now. All right, I'm going to highlight the plane. So this is the plane that I'm going to focus on. Okay, I'm going to use, this is the plane I'm going to focus on. Okay, so let me draw thicker. Okay, so this is the plane that we're going to focus on. Yeah, it's okay. I draw very thick deliberately. Okay, this is the plane, right? So that is the plane, and the deformation. Okay, the deformation will occur on this plane. This is how the deformation will occur. Okay, on that plane. That's a very bad drawing. Okay, deformation will just occur, and that plane over here, this is our X, Y plane. Okay, so buckling will occur about our z-axis because the IZZ is equal to 6.95, or I put down here, use lower, select the lower I did right before already. So when that's the case, we also know our Z. Okay, our RZ is equal to 34.9. So you don't need to calculate. It's okay. So we know that our RZ is equal to 34.8 times 10 to the power minus 3 meters. Okay, so these are from the table. Okay, so the next thing that we want to see on this is if you look at how the loads are applied, there's no resistance. So moment at this end is equal to 0. Moment at this end is equal to 0. So if moment is equal to 0 at both ends, so they are both what? Pinned. Okay. So go back to our figure again. Both are pinned. Okay. So we know that both are in a pin configuration. Okay. All right. Both ends are pinned. So we also know this now. Okay. So we know that our LE, or we just write both ends, are pinned. So LE is equal to L. Okay. So L is equal to 3.8 meters. Okay. So what else do we need to know? Okay, that's all the information that we have. Again, the most important thing is what radius of gyration to use. Okay, what's values of second moment of area we should use. And then the next thing we can find out that we need also area, right? So the area, wait, you guys must be wondering, Eugene, why do we need to know our area? Okay. Wait, because we are going to calculate our critical load. So we need to know our area, because on the y-axis over here is the area. Then we can find our load. Okay. So we are given the area, which is equal. So the area is 5700 times 10 to the power minus 6 meter squared. Okay, so that is our area. So before we go, so let's look at this chart. Okay, let's look at this chart. So this chart have what do we need? Okay, so we know that we can use this chart because the yield strength is equal to 250 times 10 to the power 6. The Young's modulus is 200 times 10 to the power 9. Okay, so 200 times 10 to the power 9, and the U is equal to 250 times 10 to the power 6. Okay. Then the next thing that we can we need to determine is we have to find out what is our LE over R, and then we also have to determine what is our EC over R squared. Okay, so EC over R squared, the 0 is based on, in fact, this chart looks familiar once I highlight. So this is EC over R squared is equal to 0. Okay, you follow this line. And then over here, EC over R squared is equal to 1. You follow this line. Okay, so we have to determine, or in order to use the chart, right? In order to use the chart, must determine our LE over R. So our LE over RZ, so our LE is 3.8. So everything is in meters. RZ is 34.8 times 10 to the power minus 3. So LE over R, so 3.8 divided by 34.8 power minus 3 is equal to 109.2. Okay, 109.2. So you will ask me, okay, so what does this mean? Okay, so 109.2. So I'm going to draw a line on this chart now. Okay, again, this is just an eyeballing. Okay, so 109.2. Okay, so this is the line. So this 109. So half 115 is here. Okay, this is about it. Okay, so this is my line. This is 109. Okay, 109.2. Okay, and then the next one, we have to find out EC over R squared. Okay, so we have to determine our EC over R squared, right? So the E value is given, right? Given the question, E is 12. Okay, so 12 times 10 to the power minus 3. Now, let's do the easier one. Okay, the R is easy. Is 34.8 times 10 to the power minus 3 squared. Now it's the C. Okay, so we know, that's where labeling, we know that this is our ZZ, right? Our ZZ direction. Okay, so this is our ZZ. Let me highlight. I do apologize, and let me write bigger. Okay, so we know that now this is not our XX. This is our ZZ. Okay, and we know that this is our ZZ. Okay, so what is C? Okay, C is the distance furthest away from the ZZ axis. So it's basically this distance down here. Okay, so this is the distance, which is C. So C is equal to BF divided by 2. So BF is equal to 0.148 divided by 2. So important. If you use the wrong one, then yeah, your answers are wrong. Okay, or you don't know what values to use. Okay, so this is equal to 0.148 divided by 2. Okay, so this is a C value, because we are the buckling, the radius of gyration is about the what? ZZ axis. Okay, so this is equal to 0.148 divided by 2. So from here, we calculate our EC over R squared. Okay, so 12 power minus 3 times by 0.148 divided by 2. divided by 34.8 power minus 3, divided by 34.8 power minus 3, the value is 0.733. Okay.